Good morning. I'm going to tell about recurrence relations. Actually, recurrence relation is used to measure the time complexity of algorithm which is involving recursion. So, topics of actually overview of the talk is analysis of the algorithm, and then why we are under then recurrence relations and types of recurrence relations, and then various possible solutions. So actually if you talk about analysis of algorithm, there are two kind of procedure: iterative procedures involving loops and recursive procedure which is involving recursion. So let us have one example of iterative procedures like C. Consider a single C program where I is getting 1 and there is a for loop from 1 to n, and I'm just writing a simple instruction print I. So if we look at the time complexity of assignment statement, as we know that its time complexity is 1, and since this is a loop, if we see it is like loop counter variable is making arithmetic progression like see 1, then 2, and then 3, 4. If we go up to I, and now I is failing when I equal to n plus 1. So if we compute this using arithmetic progression, nth term is given by a plus n minus 1 into common difference. So what will happen? So if a is first term and we are interested in ith term, into common difference is 2 minus 1. So actually this is I. 1 plus I minus 1 become I. So I equal to n plus 1. So that's why it is written over here that this is running up to n plus 1 time. And if we take n equal to, let's say 5, 1 less than or equal to 4, 5, 2 less than or equal to 5, up to and so on, when I becomes 6, it is failing. So generally any time of any type, body of loop is always running 1 less than the number of loop itself. So because it is running n plus 1 time, and so its running time of this statement is n, and itself its time complexity is 1, so it will be equal to 1 times n. So if we sum up all the complexities, it will be 2n plus 2, which is equal to big O of n, right? So another example of logarithmic loop. So if we talk about another example, see here I is updating in the form of multiplication 2 times I. So if we talk about this is not time complexity, look at here how I is increasing. I is increasing in the form of 1, 2 and 4 dot dot dot, and I will fail when it is equal to n plus 1. So actually this is GP, geometric progression, where ith term is nth term is given by a r to the power n minus 1. So a is here 1 and into common ratio is 2, and we are interested in ith term. So I minus 1, it is equal to n plus 1. So I minus 1 is equal to log n plus 1 base 2. So therefore I is log n plus 1 base 2. So this is actually 1 plus, so its running time is 1 plus log n base 2. This is its running time. So actually where this is either floor function or ceiling function, but here we take it as a ceiling function. So its running time will, this state, its running time will be log 2 n plus 1. So if we sum up all the times, we will see that this running time of this algorithm is proportional to log n base 2. So let us have another example of Fibonacci sequence. If you look at here, this is constant, its running time is 1. This is also constant, its running time is 1, and all of them they are constant, but this its running time is n minus 1. If we sum up all the times, we will see that overall time is equivalent to big O of n, which is linear in nature. So what about recursive procedure? Recursive procedures time is not easy to compute because of recursion, and we know that computer is evaluating recursion with the help of stack. So consider this example of calculating Fibonacci sequence. Fn, we know that Fibonacci sequence is defined by 0, 1, then 1 plus 0 is 1, 1 plus 1 is 2, and 2 plus 1 is 3, and 3 plus 2 is 5. In fact, it is defined as f0 equal to 0 and f1 is 1, and nth term is denoted by fn minus 1 plus fn minus 2. So actually this is forming a recursion where nth term is being expressed in terms of n minus 1 and n minus 2. So this is recurrence relation actually, and this cannot be, its running time cannot be computed in terms of iterative procedure. So remember, we need to decrease it. If we are not decreasing, it will not be forming a recurrence relation. Like see this is recurrence relation, but this is not a recurrence relation because this Tn is equal to T3 Tn by 2. It is not decreasing. Right hand side is not decreasing, it is increasing rather. So there are two kind of recurrences actually. First one is homogeneous recurrences, where we can write in this form, and right hand side of the recurrence is 0. And for example, consider the Fibonacci sequence example. Fn was written as fn minus 1 plus fn minus 2. If you take into this side, fn minus 1 minus fn minus 2 equal to 0. So here this k is equal to 2. So so what is objective of recurrence relation? So like our objective is to solve the value of fn in so that we can directly get in terms of n. There is no need to go back and again. So like see here, if we like solution of this recurrence is given by fn equal to this. We'll know how it is coming later on, not today. So fn, like see, if we put fn equal to f0 0 here, we can say that this is equal to 1 upon root 5, and this to the power 0 is 1, and this to the power 0 is 1. So this means that 1 minus 1 is 0, and now f0 is coming to be 0. So same thing we can calculate f1 also by putting n equal to 1 over here directly. No need to be going again and again. So like see, if we are interested in getting f2 from here, we have to apply the recurrence formula. f2 is f1 plus f0. So again we need to compute f1 and we need to compute f0. But here there is no need to go back to the recursion. We can directly put f6 over here, we can get the value. So second category of recurrence is inhomogeneous recurrence, where right hand side of the recurrence relation is not 0. So we are going to solve both kind of recurrences. So various solutions are there. First is master method, second is recursion tree, and third method is substitution method, and fourth is method of characteristic equation. So among all of the methods, master method is very popular, and recursion tree is also very popular method. So actually master method is used to solve only a specific recurrence which is taking this form. Tn is a Tn by b plus fn. What is this recurrence? Where actually this is divide and conquer approach, where problem of size n is divided into a part, each of size n by b, and fn is time to combine and divide the problem. This is asymptotic positive value, and a should be greater than or equal to 1 and b should be less than 1. B should be Yeah, so this is the limitation. B should, so B should be greater than 1, not less than 1. B should be greater than 1, strictly greater than 1. If B is not greater than 1, it will not decrease the value, and hence it will not form a recurrence relation. And here n by B is either ceiling function or floor function. So let us have an example. Tn is 4 Tn by 2 plus n. So now if we compare this recurrence relation with standard relation, we see that A equal to 4 here and B is 2. Now A is 4 which is greater than or equal to 1, and B is 2 which is less than, B is 2 which is greater than 1. So that means this is a valid recurrence, and Fn can be any positive value, any asymptotically positive value. So this is valid recurrence. On the other hand, if we look at it, Tn is 4 Tn by T3n by 2, and look at here, B over here is 2 by 3, which is less than 1. So this means that this is not a valid recurrence. So there are three cases of the master method, case 1, case 2 and case 3. So actually if we see the master method, Tn is ATn by B plus Fn, where A greater than or equal to 1 and this guy is greater than 1. So this is also greater than 1. So there are three cases. Actually, case number 1, we compare Fn. If we compare Fn, if Fn is big O of n to the power log A base B and minus epsilon, where epsilon is any positive value not equal to 0. If we can say that Fn is less than or equal to this value, then we can say that okay, Tn is theta n to the power log A base B. Direct solution can be obtained if we can get this inequality. If this is satisfied, we can get direct solution by using master method case 1. Like see, consider this example 1. Tn is 4 Tn by 2 plus n. Now A is 4 and B is 2 now. So n is big O of n to the power log A is 4 and B is 2 minus epsilon. So we can say that here n is 1 and this is n to the power 2 minus epsilon. So at least we can get 1 epsilon such that this guy is less than or equal to n to the power 2 minus epsilon. So by the solution of this recurrence, since it is true, we can get epsilon equal to 1. Therefore, Tn equal to theta n square. Consider another example, number 2. Look at here, Tn is n and n to the power log A is 1 here, log 1 base 3 by 2. B is 3 by 2 over here. So what will happen? Log 1 any base is equivalent to 0. So now n left hand side is n and this is n to the power 0 minus epsilon. We know that n cannot be less than or equal to this value. N cannot be less than or equal to this value. So therefore, master method case 1 is not applied over here. So another example, if we see that here Tn is 7 Tn by 2 plus n square. Now this is n square and now n to the power big O of this, we are checking whether this is true or not. Case 1 is applied or not. So n to the power log A is 7 and B is 2. Yes, this is equivalent to 2.8 something. So definitely n square is less than n to the power 2.8. Even we can subtract a small value. Let's say 0.1. We can get many epsilon. Not necessary that we are getting only 1 epsilon. So that means case 1 is applicable. Hence Tn is given by theta of n to the power log 7 base 2. So anytime if case 1 is not applicable, we look for case number 2. So what is case number 2? We are comparing Fn. First case was discussing about big O notation, and second case is discussing about theta notation. In case 2, we are comparing Fn with n to the power log a base b and multiplied by log n to the power k, where Lg stand for log 2 base. So if this condition is satisfied, then we say that Tn is theta n to the power log a base b, and log whatever value of k is over here, we can increase k by k plus 1. So let us have an example. Fn is n square and theta a is 4 and b is 2 log 4 base 2. And we can say that this is n square and this is also n square. So there is k will be equal to 0. So now n square equal to n square. So our k become k is 0. Our k equal is 0. So what will be answer? Answer, both sides are equal. So answer will be given by n square n to the power log a base b. And since k was 0, so this is 0 plus 1 become n square log n. So answer is theta n square and log n base 2 actually. Let's have another example. Case like Tn is 4 Tn by 2 plus n cube. Here n cube is not equal to n to the power log a base b. And this is n square and this is n cube. So n cube is always asymptotically higher than n square. So case 2 is not applicable. So another case number 3. Actually in case 1 we are talking about big O notation and case 2 theta. So case 3 is automatically checking lower bound like omega notation. So what is happening over here? We check for Fn. If this is greater than or equal to this value n to the power log a base b plus epsilon. Remember, epsilon has to be greater than 0. It should not be even equal to 0. That means this guy should be greater than or equal to this value. So if this is the case, then we are checking another condition in case 3 also. That is called regularity condition. And what is regularity condition? That a Fn by b should be less than or equal to c Fn. This is the regularity condition. A Fn by b. Apart from this regularity condition should also be satisfied. So in this situation, if this is true for any value of c which is less than 1, then we can say that Tn is theta of Fn. Actually, that Tn, we started with Tn, a Tn by b plus Fn. So its meaning is that actually case 3 is saying that okay, Fn is having more time as compared to this. So that's why overall time is proportional to Fn. Let us have an example. Now Tn is 4 Tn by 2 plus n cube. Look at here, a is 4 and b is 2. Fn is n cube. Now n cube is greater than or equal to n to the power 2 plus epsilon. Definitely n cube is asymptotically higher than 2 plus epsilon. We can say that epsilon equal to 1. Yes, that means number 1 condition is satisfied. Second condition was a Fn by b should be less than or equal to c Fn, right? And c should be less than 1. So if you look at here, a is 4, Fn by b, Fn by b, b is 2 over here, less than or equal to c, and Fn is n cube, right? So 4 Fn by 2 is n cube by 8. Fn is n cube. So Fn by 2 is n cube by 8 and this is cn cube. So yeah, so this become 4 n cube by 2 less than or equal to c n cube. It will cancel out. So 1 by 2 less than or equal to c. Therefore, C equal to 1 by 2, which is less than 1. That means regularity condition is also satisfied. Hence, by master method case 3, Tn is approximated by theta nq. So there are cases that there are some example when master method is not satisfied actually. So like say, let us have one example. Tn is 4 Tn by 2 plus n square divided by log n base 2. We can see that here A is 4 and B is 2. So this guy is becoming n square, no problem. And Fn is n square log by n square by n square by log n base 2. So it should be greater than or equal to big omega of n to the power 2 plus 2 plus epsilon, and which is not possible. So that's why it is not master method case 3 is not applied over here. So there are situations that even master method are any one of the case 1, 2, 3 of master method is not going to be applied. So what will happen? Then we come to the recursion tree method. Like see, this is recursion, and recursion tree method is more general than master method. In fact, master method has been derived by the recursion tree method. Consider one example. Tn is Tn minus 1 plus n. What will happen? So in this recursion tree method, this Fn is going to be root node, and this Tn minus 1 will be here. Fn is going to be root node and this Tn minus 1 will be here. Again we start breaking. N is here, Tn minus 1 from here will be Tn minus 2 plus n minus 1. If we look at here, Tn minus 1 will be Tn minus 2 plus n minus 1. So we can expand this again to get n minus 1, and this become child node. So this will continue again in this n minus 1 and again n minus 2, and this will become Tn minus 3. So in recursion tree, actually this is going to be continued like this until we get 1. So this will continue n minus 1, n minus 2, and ultimately we are going to terminate it by 1. So it will be T1. So this is the leaf node, and up to here it is not a leaf node. So in recursion tree method, we are going to add cost of non-leaf plus cost of leaf node. So total cost is given by cost of non-leaf node plus cost of leaf node. So we can see that cost of non-leaf node is this and cost of leaf node is 1. So assume that T1 is equivalent to 1. So this is forming arithmetic progression. So if we remember, sum of arithmetic progression is nth term n by 2, 2a plus n minus 1 into common difference. So because from 2 to n there are n minus 1 term, so it will be n minus 1 by 2, 2 into first term is n, so plus n minus 1 into common difference is equal to minus 1. So if we solve it, we can see that this is n minus 1 by 2, 2n plus n minus 2 into minus 1. So after solving this, we can say that this is equivalent to big O of n square. So this is why it is very popular. Recursion tree is more popular than master method, because we cannot solve this recurrence by using master method. So another example of this recursion tree, we can say that Tn is 3Tn by 4 plus Cn square. So as a policy matter, we are just writing Cn square over here, and this has 3 children. Look at previous example. This was not having any child. So this is 1. So that's why we are not making many children. But here, if you look at here, this has 3 children, each has size n by 4. So Cn square is sitting over here, and Tn by 4, Tn by 4, Tn by 4, they are 3. So again, if we start expanding Tn by 4 from here, so Tn by 4 will be 3T n by 4, that means n by 16 plus C n by 4 square. So if we look at here, 3T n by 16 plus Cn square by 16. So what will happen again, this guy will be here, Cn by 4 square and all this thing, and this Tn by 16 is sitting over here. So ultimately this is going to be up to T1. This is going to be reduced up to T1. So same thing we did in the last example, that okay, we are going to sum the leaf node and going to sum the non-leaf node. So you see here, this is Cn square, cost of this is Cn square, and this is 3 by 16 Cn square. So ultimately this is going to be terminating like T1. So before T1 it is non-leaf node and this T1 is leaf node. In recursion tree example, you need to know two things. First one, how problem is reducing. If we can say that problem is always reducing in this form, n by 4. So first one, problem was n by 4, and if you look at here, problem become n by 4 square. So at ith level, problem is reducing in the form of n2 by 4 to the power I. So now this can be equal to 1. Here it is becoming equal to 1. So from here, n equal to 4 to the power I. So from here we can say that I equal to log n base 4. So yes, I equal to log n base 4. So this is how it is coming. So yeah, and second thing in recursion tree, we need to remember that how many children a particular node is having. Like this node is having 3 child, this is also having 3 children, right? So in fact, at ith level, it is like increasing in the form of I, 3 to the power I. So if you want to count out how many T1, so they are actually 3 to the power I is log n base 4. So we can change this. So actually it will become n to the power log 3 base 4. So that is how we need to know number of T1. So as a policy, again, if you want to add all the nodes, right? So this is like how many they are, 3 by 3 to the power I. So I is like Cn is this, we are going to add them. So this is non-leaf node and this is leaf node. So if you start like from I from 0 to this, because we have this is not non-leaf node, they are from 0 to I minus 1, and I minus 1 is log n base 4 minus 1. So actually we are adding them here. So 0 to I minus 1, and in fact we are interested in asymptotic upper bound. So that's why we are saying that this is smaller than this. So if you add it together, this is forming a GP. So this will become 1 upon 1 minus R. So ultimately its running time is big O of n square, which this time can be verified by the master method also. So this was all about recursion tree method. So that is the end of the lecture.